This is the last topic of this chapter, and the title is the boundary condition. Here, a question arises: what will happen if we have electric field, magnetic field, displacement current, and auxiliary field? This is also a magnetic field. We have these four kind of fields: electric field, magnetic field, displacement current, and this H. Then what will happen if the electric field, magnetic field, and these four fields are propagating from one medium and enter to the another medium? So what will happen to the components of these fields? I have written the question. The question is, if we have electric field, magnetic field, D and H field, if these fields propagate from one medium to another, then which component of these fields is continuous or discontinuous at a boundary between different media? This is the question. And for this, we, we will use the Maxwell's equations. The two, if we have a closed surface, if we have a closed surface S, then we will use the Maxwell equation. The two Maxwell equation are in the integral form. One is d dot dA, which is equal to q free charge, and the other one is b dot dA integral, which is equal to 0. And we already know about these two equations. So if we have a closed surface, then we will use these two equations and find out what the component of D and B is continuous or discontinuous. Let's suppose we have a surface, a closed surface S, and we pick a pillbox, a small pillbox, this pillbox. Then this area, you see, this area which D is parallel, and the lower area D2 is also parallel. This is D1, this is D2, and the area remains the same. But here, this area, the flux is negligible. So I have written this is a pillbox. The area, this shaded area, the black shaded area, this is the flux through the black shaded area. D perpendicular will pass, and here D parallel, the is negligible. This one, this here the D is parallel and this is perpendicular. Now the area A and D1, these are parallel, and A and D2 in the down area. So I have written applying the this one D dot dA, previously I have written, and Q charge enclosed. I have to use this Maxwell equation to the tiny Gaussian pillbox, to this pillbox. Here in the pillbox, A is parallel to D1. Here the area is parallel to D1, and the upper surface, this is the upper surface, and A is parallel to D2, and the lower surface, there, this is the lower surface. This one is D1 and the other one is D2. Then using this equation, we can have D1 dot A minus D2 dot A. This minus comes due to the opposite direction, because one area is in this side and the other area is in this side. So the minus, there will come a minus between these two areas. So d1 dot a minus d2 dot a, which is equal to sigma free a, because sigma free, this is actually q free divided by a, charge per unit area. And if we find out q free, then it will multiply. So I have put the value of this q free, then sigma free a. If we remove the area from both sides, then d1 minus d2, which is equal to this. And here d1 perpendicular minus d2 perpendicular, which is equal to this thing. Here I am not talking about d parallel. I'm looking for the d perpendicular. D1 perpendicular minus D2 perpendicular, which is equal to sigma F. And this is not equal to 0 if D1 perpendicular is equal to D2 perpendicular. It means that D1 perpendicular and D2 perpendicular will continues at the boundaries. But this is not equal to 0. There is some charge density. Due to this charge density, discontinues when d propagate between the boundary of two media if there present a free current density, this one. If we have no free current density, this is equal to 0, and d1 perpendicular must be equal to d2 perpendicular. Then the 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 d component, the d perpendicular component will continues in this case if sigma free is equal to 0. But now this is not equal to 0. It means that this is the d perpendicular component as discontinuous at the boundaries between two surfaces. Similarly, we are using the second, I have presented this as the second equation, which is P dot dA for the closed surface, which is equal to 0. Here, using this pillbox, then B1 dot A minus B2 dot A, which is equal to 0. And here the B1 perpendicular minus B2 perpendicular, which is equal to 0. And B1 perpendicular is equal to B2 perpendicular. This shows that B will continues at two boundaries, because B1 perpendicular is equal to B2 perpendicular. It means that the B is continuous at two boundaries. So this is the two equations, and we are using this for a closed surface S. Now, for any surface S bounded by the closed loop P, this is any surface S, and this is bounded by a loop P, we will use the integral form of Maxwell's equation as we will use the third equation and the fourth equation. And here we have a closed loop, and we pick this small surface, and I have shown here, and this area is very small, and then no flux pass to this area. And here the current is flowing in this direction. This is E1, and back this is E2. Then E1 dot L minus E2 dot L. We will use this equation number third. Then E1 dot L minus E2 dot L, which is equal to this one. But here the flux, the magnetic field is 0. This area is very small, and no flux pass through this area. Then it means that this is equal to 0. Then finally I have written that E1 parallel dot L minus E2 parallel dot L, which is equal to, this will be equal to 0. And finally, E1 parallel, which is equal to E2 parallel. It means that E parallel component of electric field will continues at two boundaries. E parallel will continue. Similarly, if we use the fourth one, H1 dot L minus H2 dot L, which is equal to I free, and this part will be equal to 0. And for this surface, here I free, this I free current is equal to Kf, and N is the normal, and L is the length of this, and I free will be equal to this. And finally, if I put the value of I free this, then from this equation, the H1 and H2 parallel, if we, this is, if we say that this is parallel and H2 parallel, this is not equal to 0. It means that the H component, the parallel component of H, is discontinuous. Now, if we have a linear media, for example, in case of linear media, D1 perpendicular minus D2 perpendicular. For a linear media, we have D, the displacement current. This is equal to epsilon E, where epsilon, this is equal to epsilon naught into 1 plus chi. And we also know that D is equal to epsilon E, where epsilon is the permittivity for an object for the linear media, which is equal to epsilon naught into 1 plus chi. E chi is the electric susceptibility. Then the first equation, we can write down epsilon 1 E1 perpendicular. There will be no change, and B1 perpendicular will be equal to B2 perpendicular. The third, E1 parallel, which is equal to A2 parallel, this will be the same. And the fourth equation that we have derived, if we put H is equal to 1 over mu B, and then 1 over mu1 B1 parallel minus 1 over mu2 B2 parallel, which is equal to this one. Then here we can say that if we have a linear media, E1, the electric field, the perpendicular electric field will discontinues. The magnetic field will continues. The electric field, the parallel component of the electric field will continues, and similarly the parallel component of the magnetic field will discontinues. Now the point is, if we have no free charge density and no current density, in this case, what will happen? What will happen to the components of these fields if we have no current density and no charge density? It means that sigma and current density K, this will be equal to 0. Then in this case, we have this, if this is equal to 0 and this is equal to 0, then we have all these equations, the perpendicular of the electric field, the electric field parallel, the magnetic field perpendicular, and the magnetic field parallel, all will be equal to the same. It means that in this case, the components, these components, the perpendicular and parallel components of the electric field and magnetic field will continues. So this is the last lecture of this chapter, and now I'm interested to discuss some problems related to this chapter. Okay.